So yeah, reactions which form rings. So I'll call them ring closing or ring forming reactions. And the thing I wanted to talk about specifically was Baldwin's rules. So Baldwin made some rules about favorability for certain reactions taking place. So is something favored or disfavored, I guess, would be the word. Disfavored. And there's a classification for this, so that, for example, let's say you had an oxygen and it is bonded to and we do a reaction like this. Actually, let's erase this. This would be classified, and I'll draw some numbers here, as 1, 2, 3. So there's 3 carbons. What is the hybridization of the carbon which has got the bromine on it?
sp3.
sp3, right. So I'll just make a little thing here. sp3 carbons are classified as tet in these rules. And so this reaction here would be classified as a 3 exo tet. Okay, so 3 because it's actually, no, this would be a 4. Sorry. Oh boy, here we go. Thank God I caught that. This would be classified as a 4 exotet. So 4 for the number of atoms that are going to make the ring. Tet describing the carbon of where the ring forming is taking place. So that's a sp3 carbon. And exo, the part we don't know about yet is exo, and I'll describe that in a second. So in this reaction, our final, we would make a 4-membered ring. That would be the product, right? So let's do another one with okay, let's label this 1, 2, 3, 4, 5. 5. Okay, the hybridization of carbon number 5. The way that this reaction is going to work is So this is going to attack that carbon, and these electrons are going to move out. So carbon 5 is
SP2.
yeah, sp2. And so all sp2 carbons are classified for whatever reason as trig. Oh, I know why. Okay, so this reaction would be classified as we got 5 carbons, or 5 atoms, so 5. Again, this is exo. And in this case, it would be trig. I'll do one more example, and then maybe we'll see what the other part, this orange thing, means here for a second. So number is just the number of atoms which can make up the ring. The carbon which the bond is being formed at, carbon 5, is, in this case, it's an sp2 hybridized carbon, so it's trigonal. So it's going to be 5-exo trig. And another example here would be, say, this one. Oh, let's try this. And here we have 1, 2, 3, 4, 5, 6, 7. So this type of cyclization would be classified as a 7. Endo. And the carbon here, carbon 7, is sp. And so all sp hybrid carbons are called digs. So a 7 endo dig. So there's 2 basic ways that these rings can form. Endo, like if it's exo or endo, and if this might not be clear the way that that it's drawn, but if you've got a, move over here for a second. If you've got your nucleophilic end and you've got a chain, if the way that the nucleophile attacks and the electrons come back into the ring, so we're going to put some electrons there, this would be an endocyclization. And if the nucleophile attacks and the electrons are moving outside the ring, this would be an exo. Another example would be, say, nucleophilic end. So if this attacked in such a fashion and those electrons move outside, this would be exo. And if they attacked on the end here and it became still part of the ring, this would be endo. So that's basically how these types of things work. I don't know if it's hard to visualize this with the sp3 hybridized, like a TET, because the leaving groups are the electrons are moving out as the leaving group leaves. So it's hard to visualize that one. But for the trig and the dig, I think it's not too hard to see. So if we had something like this, would this be endo or exo?
Endo.
Yes, so this would be an endo one because there it's still part of the ring system. Now, if we did if we change this up a bit, so we had those electrons are moving out, this would be exo. So so what Baldwin's rules actually say is it's basically they tell us if things are favored or disfavored based upon the classification of the ring size. Is it an exo or is it endo, and the hybridization of the carbon. And I guess the key thing to remember for Baldwin's rules are that these are assuming things are under kinetic control. So in the presentation we did last class, there was a couple of we made a couple of carbocycles in that reaction. So one of the things you could do if you were interested in is going back and looking at it and seeing if do these follow Baldwin's rules or not. So yeah, just that would be something which would be interesting to do. Okay, so let's see which ones are favored and stuff like this. So essentially all exo tet are favored. So some nucleophile, internal nucleophile. I guess I shouldn't make that chain that big, but if you've got some leaving group, all of these types are going to be favored. So all X doesn't matter on the ring size, and so this is a all exotet. So similarly, all exotrig cyclizations are favored. So nucleophile, say I'll draw oxygen there for whatever reason. And so all of these ones will also be favored. Okay, yeah, this was a good one. I do have an example here. Okay, so 5 and 6. Endo tet are, I should write this in red, disfavored. So how could we have this? Here's an example. So if we've got a, for example, one, two, three, four, five. Let's pretend that we had a some sort of ester or some darn thing. And we wanted to do, and I should actually make this so it's on, put some methyl groups there so it's not. And we wanted to do this reaction here. So we've actually got a leaving group, which would be part of the system. It's not quite, we're not actually necessarily making a ring, but if we're doing this reaction, it's coming back on itself. So these electrons are coming back on itself, but this is a disfavored reaction. It doesn't happen. So this is, I was trying to figure out how do you draw one, but yeah, came up with that. So something like this, these are disfavored reactions, and we'll see in a while why they would be. Does anyone have an idea as to why these would be disfavored? It has to do with the fact that if you've got a if it's a tetrahedral carbon, let's say it's bonded to an oxygen, we could even make it a better, yeah, let's draw this. 1, 2, 3. Oh, we need another carbon. So if we're trying to break this bond here, the antibonding orbital for this is, of course, on the opposite side of the carbon. And I've actually drawn this linear, so it's not quite a fair representation, but let's pretend that it's actually drawn on an angle. So sulfur. And the antibonding orbital would be here, sigma star. Because these electrons have to get into the sigma star to break this bond. And there's not enough, the geometry isn't there to actually make it work. So that's one of the reasons why it's hard to do this. They're not kinetically. If there's another way the reaction can take place, it'll take place faster. So yeah, these are because it's under kinetic control. This would be not a favored reaction. Some of the other ones that are disfavored. Draw this in red. Three, 4, 5. Endo-trig, disfavored. You can find the odd exception to this rule somewhere, and if you do, that would be super. But these ones are all disfavored. But conversely, 6 are favored. Once you get the ring system slightly bigger, they become kinetically favored. So 6 and 7 endo-trig are favored. Now, what is interesting is that if we move on to the dig reactions, is that I'll draw this in blue. This one's all endo dig reactions are favored. So this, when you look at something, you might say to yourself, wait a second, this doesn't make any sense. So this would be a favored cyclization. So yeah, so this one would be favored, and the reason why is that the because of the because of the triple bond, the nucleophile might not have been able to reach, say, these orbitals, but they can reach, I guess I'll draw it in black and red. They might not have been able to reach, say, those orbitals, but they can reach these ones that are right pointing towards them. So the way I've drawn this mechanism here is could be slightly wrong in the sense that these second arrows here, star and star, might not happen immediately. The first one might go and then the molecule might rotate slightly to allow the overlap. But you've got accessible orbitals because it's planar, pointing towards where the nucleophile might be. So if this is attached, for example, there might not have been the geometry to come underneath it, but sideways, the approach. So that's one of the interesting things is that these guys are all favored reactions. The 3 to 3 and 4 exo dig are disfavored. But when you get to larger ones, 5 through 7 exo dig are favored. So what we'll do at the start, we got 2 hours on Thursday. So I'll start the we'll do the prostaglandin synthesis. At the start of it, I might draw some real world examples of some cyclizations, and you can tell me if they are, what the classification might be, and remembering which ones are favored and disfavored can sometimes be excess information in your brain, which is hard to remember. But some of them will become second nature. There's in a while, because we'll see them repeatedly over and over and over again. But yeah, just basically as a word of caution, these are for kinetically controlled reactions, not necessarily thermodynamically controlled reactions. So there's some really classic examples of reactions which are controlled thermodynamically, which would straight off break some of these rules. You'd say, wait a second, this one's this, and we know that it happened, so what's going on? So that's just the word of caution, that this is for kinetic reactions. So if you look at our synthesis of our last one, just think about the rings that were formed, and do they follow the rules or not? And were there any other potential ways that the reaction could have taken place? And would have they broken the rules? But yeah, and then we'll start the prostaglandin synthesis on Thursday. Were there any questions at all?